Most of the time, we launch rockets with the pointy end up. Sometimes, we strap rockets to the belly of commercial airliners and drop them over the ocean. Next on the Rocket Ranch.
EGS Program Chief Engineer, verify no constraints to launch.
3, 2, 1, and liftoff.
Welcome to space.
As we're recording this, we're in the throes of the launch campaign for the Ionospheric Connection Explorer, or ICON. We'll get back to the science of the mission in a few minutes, but first, we wanted to take some time to talk about a one-of-a-kind launch capability. This launch is managed by NASA's Launch Services program, and they selected the Pegasus XL rocket, manufactured by Northrop Grumman. Here's Phil Joyce, Vice President, Space Launch Programs, Northrop Grumman Innovation Systems. All right, I'm now in the booth with Phil Joyce. Phil, thank you so much for joining me today.
It's great to be here.
And we're glad to have Northrop in town. We're glad to see this Pegasus ready to fly. I want to kind of back up a little bit and learn more about you and kind of your history. You've been with Pegasus for quite some time now.
Yeah, well, I've been with Orbital Sciences, now Northrop Grumman, since 1992, so a 27-year veteran of the launch vehicle business with a career that spans a lot of different launch platforms. Pegasus is one of the platforms in my portfolio today. I have the small launch vehicle area at Northrop. Pegasus is a world-class launch vehicle, the first privately developed launch vehicle back in the day, with the first flight in 1990.
Okay.
And also, of course, as you noted, a very unique launch vehicle in the fact that it is air-launched, and it was the first air-launched space launch vehicle ever constructed. With the first flight in 1990. This will be our 44th Pegasus mission.
Awesome, congrats. So are you an engineer by trade?
I am. I'm an aerospace engineer.
Have you had any personal favorite missions or favorite moments in your career?
Well, it's hard to top flying to the sun. So when we did the upper stage to Parker Solar Probe and delivered that spacecraft just on the bullseye,
cool.
That was a wonderful experience. But every launch is the same. It's all adrenaline. It's all that nerves just before ignition. Pegasus missions are no different, and certainly they feel as intense as any of them.
Cool. And so I want to make sure that we don't overlook the airdrop fact, because I think that's what makes this the most unique. So help give people that are listening to this kind of a visual for what does that mean when we say airdrop?
Well, airdrop can be done in different ways. We do it in a way that really boosts the performance of the system. You take a launch vehicle, which is a combination of propulsive stages with a payload on the front underneath a payload fairing. And in our case, we take that on the L-1011 up to a launch condition, which actually adds a lot of energy to the equation. And,
sure.
and that energy that the L-1011 delivers, which is an altitude of something like 40,000 feet and a drop speed of something like Mach 0.8, is actually our first stage, and it doubles the payload performance of the rocket compared to if you launched it on the ground. So
L-1011, for our younger viewers who may not be familiar, I think you guys have titled yours the L-1011 Stargazer, is that correct?
That's right, Stargazer.
So what is the L-1011, just for people who have never heard of it before?
So the L-1011 TriStar used to be a commercial airline, a wide-body airline that was used for commercial air travel. We purchased that aircraft back in the early 90s. We had to beef up the structure of the airplane to carry the Pegasus XL launch vehicle, which weighs about 57,000 pounds. So a standard commercial airline could not handle that kind of a load, and so we beefed up the structure of the L-1011 to be able to carry the load as well as to drop the load. So there's a pretty sophisticated hook release mechanism underneath the aircraft that interfaces with the Pegasus rocket.
Cool. So you talk about beefing up an airplane. So when I walk on board this airplane, historically used for commercial airline purposes, am I going to see first class, coach, the whole kit and caboodle inside?
Yeah, well, we don't make our team sit in the back. We don't make them sit in coach. They're sitting in what used to be the first class section. But of course, it's been heavily modified to include our launch panels for controlling the rocket systems, all the systems on board the Pegasus. We have launch panel operators that fly out to the launch point and monitor the systems on the rocket real time, as well as the payload systems are monitored from consoles up in that first class area. The entire back end of the aircraft has been cleaned out of all the seats and all the overhead bins, and we like to refer to it as the bowling alley back there. It's just a long open.
Do you bowl back there?
No. But it's empty, and that gives us additional performance capability to launch this amazing machine.
Can you launch anywhere in the world? If you're on an airliner, I would think that anywhere you can leave a runway from, you could?
That's right, and that's the true advantage of an air launch system. It gives you that global flexibility. In fact, we've launched Pegasus from the Canary Islands. We've launched it from the Kwajalein Atoll out in the middle of the Pacific Ocean, as well as more conventional launch sites like Kennedy Space Center and Cape Canaveral Air Force Station. So it truly is an independent launch platform that gives us lots of flexibility and really enables Pegasus to deliver payloads to any inclination.
Cool. So for this launch, if I remember correctly, we were actually supposed to launch from the Kwajalein Islands. Is that correct?
Yeah, that's right. The original launch attempt was designed to go out of Kwajalein, and that was because we get a performance boost by launching near the equator.
Okay.
Rocket equation helps you understand that. The closer you are to the equator, the more the Earth's rotation helps you.
Sure.
And it turns out that we really didn't need that performance, that the Icon spacecraft came in significantly under budget on mass.
Okay.
And so that enabled us for this launch attempt to come back here to the Cape, where logistically it's a much more straightforward operation.
I think about launching a rocket and just the orbital mechanics of blasting a giant machine into outer space and getting it into an orbit you want. Like, that's difficult. But now you're adding like all of that with the complexity of now we're flying through the air to do that. Is it harder to launch from a plane and get things where you want them in space?
Well, there's challenges with both approaches to space launch. You have additional systems though when you involve an airplane. So not only does the rocket and all its systems have to perform flawlessly in order to get to a launch attempt and to have a successful launch, but that aircraft has to perform flawlessly and all the systems on board. So it does add some complexity to it, but the payoff is that flexibility on launch location we talked about a minute ago.
Okay. And I'm assuming that this isn't the kind of thing where we have a rocket strapped to an airplane and the rocket just ignites. That seems like that would be dangerous for the people on board. So what's that process? What's the actual launch sequence look like?
Yeah, there are 7 souls on board this aircraft.
Yeah.
And so
It's
our priority,
not an uncrewed airplane.
priority at Northrop Grumman is all about those 7 people, right? And the main thing is safety, and safety is always first in our minds for any operation, particularly this one, which is more hazardous than usual. The Pegasus systems and the systems on board the L-1011 are designed to monitor all the safety systems on board the rocket and to ensure that we've got a safe condition in order to launch. When we actually launch the Pegasus, it's released from the L-1011. There's a button up in the cockpit that the pilot actually presses to release Pegasus. It's a manual operation, and if that pilot isn't comfortable with where things are, he won't release. But once it does release, it actually coasts away from the aircraft for 5 seconds. The aircraft banks at that point because it's just released 57,000 pounds. So you can imagine it's going to gain some altitude pretty quickly.
Yeah.
And it's that separation in that 5 seconds that puts the rocket a safe distance away from the L-1011 and the crew to ensure safety, which is, again, our highest priority.
Cool. So does this mean that do you have a traditional launch countdown then? If ultimately the pilot held to like when we get to 0, like you got to push the button?
He's flexible, so we don't have an auto sequencer, for example, like most ground launch vehicles will go to internal power and then go within 2 minutes or so. They'll go into an auto sequence where the computer on board that rocket is actually controlling the ignition pulse. It's monitoring, and that can be turned off by people on the ground, by operators on the ground. But everything is automated unless it's interrupted by an operator. In the case of Pegasus, the pilot has control of that event, and none of the systems to start the actual launch sequence initiate until the rocket is released from the airplane.
And for launching the rocket, again, thinking about a ground launch, you're launching from a very specific point on Earth. Do you have like one single spot in the air that like you have to hit that moment and like everything has to be perfect at that moment in space to launch?
We call it the launch box, and so the L-1011 pilots will fly, take off here from the skid script, excuse me, the pilots will take off here from the skid strip at Cape Canaveral and fly out, and then fly what we call a racetrack, which positions the aircraft at the right time, at the right place for the drop. They will align the aircraft with a drop box that's 10 miles by 40 miles long.
Okay.
And they need to be inside of that box for the actual drop and launch of Pegasus. All the mission planning, all the range safety is designed around dropping the rocket inside of that box.
So as long as you're in that box, the rocket can kind of adjust, so to speak, in flight to get where it needs to be.
That's right. The rocket will guide itself into orbit based on where it's released, and if we're going a little bit too fast or a little bit too slow, or we're 10 miles shorter than what our nominal is, the onboard navigation systems on the Pegasus will correct for that and get us into a very precise orbit.
Cool. That's great. So you personally, where are you going to be for launch? Do you have a role? Are you on console somewhere?
Yeah,
or?
I'll be in the Mission Director Center. I'm kind of a suit though, so the real rocket operators are the Pegasus launch team. The mission director for Northrop Grumman is Brian Baldwin, who is our program manager for Pegasus, and the rest of the launch team, including the launch conductor, are there in Building AE in launch control.
Cool. So I would be remiss if I didn't ask you, because Icon has been, I don't know how to describe it. We've had some delays. This time, almost exactly a year ago, it seems like we were up. The plane had taken off. We were about 30 minutes from launch, and we scrubbed out, and we're back here again almost about a year later. So can you tell us kind of what happened? What's happened over the course of the past year?
Sure. Yeah. Any space launch requires flawless operation of a highly complex machine made up of thousands of parts, software, and launch operations that must execute perfectly every launch, every time. The Pegasus Icon mission has challenged the Northrop Grumman NASA team repeatedly, but we're excited to say that we're past those challenges and are ready to go. During the previous launch attempt, engineers observed some anomalous readings on a position feedback sensor on the Pegasus rudder fin actuator. The rudder is really what steers the rocket during the first stage of flight. It's like an airplane, so it's got a rudder just like an airplane does. And it was that position feedback that looked anomalous to us and caused us to scrub that previous launch attempt. Because the mission success is our only focus, and because we did not have a clear understanding of those readings, we stood up a joint investigation team with our NASA partners to determine cause and corrective actions. Those corrective actions included removing and replacing hardware with modified designs, performing qualification testing, and conducting 3 captive carry flights to validate the hardware upgrades, including the one that we flew to ferry the rocket from Vandenberg Air Force Base here to Florida. Working through those challenges as a team was the only possible due to the outstanding 3-decade partnership we've had with NASA on Pegasus, and we are proud and honored to be here to launch.
Yeah, obviously, Northrop Grumman's a big part of our launch services program. Obviously, a big mission here with Icon. So glad to have a year. It sounds like probably a tough year, but probably feeling really rewarding now. Like as we're getting ready to hey, we did this the right way. We're going to get there.
I think everybody involved would say it was a very intense year.
Okay.
Time is of the essence in these sorts of things, and we worked almost around the clock to get to the bottom of this and what was really happening. The Northrop Grumman team working with NASA hand in hand in that activity. So it is very rewarding to get past it, to really understand what's happening, to make those corrective actions, and in fact we gained great confidence on the ferry flight from California to here, where we didn't see a repeat of any of the issues we had in the previous launch attempts.
So I'm assuming that this is a mission. Every mission is this way, but I'm sure in particular your team is excited for this launch and anxious for it. So what's that going to feel like to see this thing fly and be in orbit correctly? How's the team respond to that?
Well, any launch is all adrenaline, and it's one of the reasons we're in this business. It's a blast, right? And no pun intended. But this one in particular, because of all the effort that we've had to put in to get this right on both sides, on
Sure.
the payload side, the NASA side, and the Northrop Grumman side, the teams that solve this problem are the teams that are going to be launching the rocket. And I can't imagine that they don't have an extra boost of adrenaline for this mission compared to others, although they're all very exciting.
Yeah, so you describe yourself as being a suit. So kind of as a leader of this group, does that hold specific meaning for you and kind of like your history with the rocket?
Yeah, the Pegasus team is a family. Been together for since 1990, and a lot of the people that are working Pegasus have worked on the program for over a decade. So it's really rewarding to see them have the opportunity to get payoff for their efforts. And we know it's going to be a successful mission.
Cool. So I want to go back real fast. There was a comment you made and I heard that with the Pegasus ferry flight across the country, with a commercial airliner, if you're flying yourself from LA to Orlando, you just kind of take as straight a path as you can. But I believe I've heard that the L-1011 and the Pegasus take a very different path to get here. Is that correct?
Yes, we have to file a special flight plan with the FAA because we are carrying 50,000 pounds of rocket fuel.
Right.
So we do avoid populated areas along the flight path, but it's not all that different. The people that are riding there is about a five and a half hour flight, and we take advantage of this flight to monitor the systems on board. So it's actually a dry run for our launch attempt. Right, we've got the systems powered up. We're not arming anything or doing anything we'll do for an actual launch. But we will monitor all the systems. And in fact, we were monitoring the system that gave us the issues the entire flight from Vandenberg to Florida. And then when we get here, we actually will practice before we land on the skid strip. We'll actually practice not a launch attempt, but basically going out to the racetrack, turning our transmitters on, having the range capture that data, and it's a really good dry run, not just for the Pegasus team, but for the range as well, to make sure everything is set properly and we're ready for launch day.
Cool. Phil, appreciate you. Good luck to you and the entire team. Obviously, we're all going to be anxious to see this one fly, as with any launch, but certainly like overcoming challenges is what makes NASA and Northrop Grumman great.
Great to be here. Thank you very much.
I wrangled up another ranch hand to help track down some more information on this long-awaited mission. Here's my colleague, Madison Tuttle, with Dr. Nikki Fox, the Heliophysics Division Director in the NASA Science Mission Directorate, and Principal Investigator for ICON from the Space Sciences Laboratory at UC Berkeley, Dr. Thomas Immel.
All right, I am here in the booth with ICON Principal Investigator Dr. Thomas Immel, and we also have Dr. Nikki Fox, who is the Director of the Heliophysics Division from NASA headquarters. Welcome to you both. If we want to start out, you could just give me kind of a brief, high-level overview of kind of your role in the ICON mission. Tom, if you'd like to start.
Being the Principal Investigator, I'm responsible for the scientific output of the mission. I'm working with a team of scientists and to define the science goals, in which we have well defined at this point, and agree with NASA on what those were. And then, Berkeley was responsible for putting together the observatory. So, of course, we've worked with a number of partners on that, including Northrop Grumman for the spacecraft, and to integrate the payload, the scientific payload, with the spacecraft to create the observatory. We also worked with Utah State to integrate all the instruments on the payload, and we have instruments from Dallas, University of Dallas, and Naval Research Lab, as well as Berkeley Imagers. We were selected by NASA to do this mission in 2013, and it's been a long road, but we're finally glad to be launching it this week.
Yeah, Dr. Nikki Fox.
So in my role, I am responsible for all of the spacecraft and all of the assets that make up the Helio fleet. And so we are very excited. We have obviously missions looking at the sun, tracking all of those events all the way through the space between the sun and Earth, and then ICON joining our fleet to really look at that sort of final piece, what happens when all of that solar energy gets into our atmosphere and dumps a lot of energy there, and what is happening in that sort of very dynamic region where ICON is going to be flying through. And it's a wonderful partnership. We have a imager up there called Gold that was launched last year, and that is taking full hemispheric images from its sort of vantage point at geosynchronous orbit. And then ICON will be whipping through, making the in situ data, telling us exactly what is happening kind of out in that environment. So we can't wait.
Perfect. And how big is your team in total? Do you know how many people are involved with this mission?
Well, let's see, between Northrop and the launch vehicle, Northrop, so Northrop also has the launch vehicle as well as the spacecraft. So there will be probably 16 Northrop engineers on console at Berkeley when we launch, where the mission operations are. And then there's so many people here for the rocket, so it's hundreds of people.
Yep, we always say it takes an entire family to put a spacecraft into orbit. You just don't realize how many people, and they all have a very, very vital role. And it's, one of the beautiful things about doing these is getting to work in these incredible teams.
Right, and you touched briefly kind of what ICON is going to be doing. Could you explain to our listeners a little bit, just in general, what is the ionosphere?
Nikki, I can try. Well, the ionosphere is the region around Earth that's charged, or it's been ionized by solar radiation. That's how it gets ionized. Where that plasma goes and how it behaves after that is subject to a number of different inputs. Of course, the aurora is another place where a lot of plasma is created. That's by charged particles that initially come from the solar wind, but energize in the magnetosphere and then channeled into the high latitude regions of the Earth. That can modify the ionosphere pretty drastically. ICON's focus is on the forcing that comes from below. Most of the solar energy that comes from the sun and ends up on Earth ends up right here on the surface. And it turns out that a lot of energy and momentum comes back up. And that can come up in large-scale waves, and there's a family of waves and tides that can carry that energy back up into space. And it turns out that we think that that may be the key to understanding why the ionosphere is so variable, and then the key to being able to make better predictions of its conditions.
So, Tom, we could describe the ionosphere maybe as like a transition region. It's where all of the weather that we worry about here on Earth, the hurricanes and the tornadoes, that's kind of reaching up. And then that space weather from the sun is coming down, and it's that kind of handshake between those two different weather systems that is that transition region that's the ionosphere.
That's right. It's space weather meets Earth's weather in the ionosphere. And we wouldn't have said that a decade ago. It was sort of a surprising sort of outcome from previous NASA missions.
Yeah, that's actually true. We thought about a decade ago, we thought everything was driven by the sun. And now we're finding out that it's so dynamic and there's so much energy there that there has to be something else. It can't just be the sun. And so now we think it's actually energy that comes up from our weather. And where they meet, that's the ionosphere.
So I kind of understand that like radio communications, GPS signals also kind of float through the ionosphere. Obviously, those have pretty big implications for our life here on Earth. I don't know if you guys want to elaborate a little bit kind of the importance of this mission just for the everyday person on Earth.
Yeah, so the ionosphere is really, that does often the radio signals bounce off the ionosphere or they travel through it. And when the ionosphere is nice and quiet, then we get those signals just fine. But when we have disturbances, maybe like bubbles, really bubbles of plasma that form in this region, and they can adversely affect our ability to have these communications. And that has effects for obviously military, for FAA. We want to be making sure our astronauts are safe. They're all in this region. And so we really need to study it and understand it.
So ICON has, I think it's 4 instruments on board the spacecraft. I don't know if you want to talk a little bit about kind of each one and their role within the mission.
Well, I'll start with the wind imager. So it's an interferometer, and what that means is it takes light into its aperture, and it causes it to interfere with itself. So you can very, very carefully determine the wavelength of the light. We can determine it so well that we can determine if the emission, the place where the light's coming from, is moving towards you or away from you, simply through Doppler shift of the light. And so it's like it's like looking at someone across the room, and looking at the color of their shirt. ICON could tell you if they're running towards you or away from you by the change in the color of their shirt. So it's about 5 meters per second, which I think I can do 5 meters per second. I haven't tried. But so that's an important measurement, and also we get a temperature measurement from that as well. That looks right down, that wind and temperature we're measuring right down at the boundary of space. So we say 60 miles, it's 100 kilometers is that edge of space. And we retrieve the winds and temperatures from there continually day and night. And as at higher altitudes in the day when there's a lot of air glow, and you can retrieve that information. In the daytime also there's ultraviolet emissions where you have two ultraviolet cameras that pull out you can retrieve composition of the upper atmosphere, how it changes, and also the ionospheric density profile. We want to know where that peak in the ionosphere is in altitude and how dense it is. We also carry in situ measurements. So what's remarkable is that in our orbit that we've selected, we can measure the motion of the plasma. That the plasma is generated. You're in a magnetic field. So what's affecting that plasma is sort of everything along that magnetic field. And in fact, if you look down the field line, you'll end up at a place where we're making the wind and temperature measurements as well. So there's this sort of key observational characteristic to the mission that's not been done before.
So ICON has been a mission 6 years in the making. What challenges or frustrations have y'all faced along the way?
You don't launch unless you know everything is going to be perfect. And, so there was some anomalous behavior when we tried to launch last year, and I have to just give credit to the amazing team that really stood into this. Nobody ever gave up. The ICON team is still there, still waiting for this mission. We've even used the time to do some extra testing on the spacecraft, walking out the solar arrays, making sure everything is going to be perfect when we actually come to launch. And there's only one ICON. It's not like we are going to launch it and if something goes wrong, we're just going to build another one. There's only one ICON. And so we want to make sure everything is 100% perfect before we launch our precious baby into space. Because, it's just, we've waited a long time. We've got this incredible science we want to do. This is the mission to go and answer it. And we're certainly not going to take any chances with it. So everything good in life is worth waiting for. And we just had to wait a little bit longer.
Like Nikki said, we said, Nikki, what we have to do is we have to open up the whole spacecraft again. We have to test the spacecraft and all the instruments one more time. And, everyone at NASA understood why you have to do that. It's been some time as we had to, but we're talking to the engineers. They're very happy to have gone through that. So we're ready.
Is there anything, just from a personal perspective, what are you most looking forward to? Results from this mission, observations from this mission? Is there anything in particular you're really anxious about?
I don't think we're anxious. We're really excited. As Tom noted, we really started working on this mission in 2013, and that probably sounds like a long time, but it takes a lot of time to put these really, really sophisticated missions up in space, and you have to have everything right. And so you can't go up and fix it. You have to have everything right. And so it does take a while. It takes a village. It takes a lot of teamwork to put it together. And so I think we're all incredibly excited about seeing the science that is going to come from this mission. Really, we've really formed the right questions, I think, to be asking over the last decade, and ICON is certainly the right mission to be answering them.
Yeah, and I'm looking forward, I think, to every single little thing. I'm looking forward to the first lunar calibration of the EUV instrument. There's not a lot of good calibration sources in the extreme ultraviolet, but the moon reflects the solar spectrum very specifically in a way that we understand. So we use that as a calibration source. Stellar calibration for FUV, we're going to be looking at a star field in the ultraviolet, and the first one of those to come through is going to be super fantastic. And I'm also looking forward to seeing the first fringes in the interferometer for the wind instrument. And I want to know exactly where I'm going to be. I know where I'm going to be. I'm going to be standing over an engineer's shoulder looking at their plot when that comes through. So everything's exciting for me.
Great. I think that is all the questions I have. Is there anything you guys want to add?
I just think Tom sounds like an expectant father. It's like you say, I'm going to be there for the first steps and the first words and the first day of school, and that's just how Tom sounds, and that's kind of how you feel. It's like being a parent.
Right.
You bring them up really well, and then you send them off into space and hope they behave themselves.
Yeah, and we have competition. I always talk to the gold PI, Richard, about being first. We were always ahead in the schedule, and he's on this crazy communications platform. He's never going to get to space on that thing. He's there a year ahead of us, that guy. They did so well with that. So we're finally looking forward to being on orbit with gold.
Yeah, that partnership is going to be really great. The in situ and the remote sensing working perfectly together to really give us the answers to the questions we want.
Great. Well, we are very much looking forward to all the results that this mission yields. Dr. Nikki, Dr. Thomas, thank you very much for joining us.
Thank you.
Thank you.
Go Pegasus, go ICON.
Go ICON.
Hopefully you had a chance to tune in to the broadcast and see the launch of ICON. She was successfully delivered to space the evening of October 10th, 2019. I'm Joshua Santora, and that's our show. Thanks for stopping by the Rocket Ranch. Special thanks to our guests, Phil Joyce, Dr. Nikki Fox, and Dr. Thomas Immel. And another big thanks to my co-host, Madison Tuttle. To To learn more about ICON, including mission updates, visit nasa.gov/icon. To learn more about LSP, our commercial launch providers, science missions, and robotic explorers, visit nasa.gov/launch services. And to learn more about everything going on at the Kennedy Space Center, go to nasa.gov/Kennedy. Check out NASA's other podcasts to learn more about what's happening at all our centers at nasa.gov/podcasts. A special shout out to our producer, John Sackman, our soundman, Lauren Maythree, editor, Mike Chambers, and special thanks to Mary McLaughlin and Ken Appel. And remember, on the Rocket Ranch, even the sky isn't the limit.